Okay, welcome to Physics 125. We're going to be doing lectures via this video format. It's not the way I prefer to do it. I'd like to have you right in front of me so I can see your faces and get your feedback, but this is what we have due to the situation that we are in right now. So I'm going to record each chapter, sometimes in a single lecture, sometimes in two parts. Chapter 0 is a short chapter, so we're going to cover this one all in a single lecture. You might be wondering why we have a chapter 0 to begin with. You have a physics book that you got for this course, right? Nice, big, thick physics book. Lots of wonderful chapters about physics. And we have no problem as people who love physics understanding the physics book and all the different parts to it. But as we try to teach it to others who are not as familiar with physics, the writers realized that they needed to explain what physics was and why we should want to study it before they could start the book. But they already had the book written. You notice we're in the 10th edition. So I'm not quite sure which edition they went back and decided they wanted a chapter at the beginning and they didn't want to change all the chapter numbers. So we start with chapter 0, which if you've done any programming, you're perfectly comfortable with starting counting at 0, even though most of the world doesn't do that. So chapter 0, why study physics? Here we go. So before we can discuss why we would want to study physics, we need to know what is physics? What is physics? And if you were in class with me, I would ask you this question and I would wait very patiently until you respond. But you're not here, so we're just going to move on. What most people do know about physics, even if they've never taken a course, is they've heard of Einstein and they've heard of his famous equation, E equals mc squared. And I think that's a great general definition of physics. E equals mc squared. You got to know what that equation stands for in order to appreciate how it's a definition of physics. So the big capital E stands for energy, and the M stands for mass, which is a measure of how much matter we have. So that's really what physics is. Physics is the study of matter, the stuff around us, the stuff that makes up our world, ourselves, our universe, and also the study of energy, which is what allows that matter to move and to do many different things. So we have both the matter piece and the energy piece, and we also have how the two are related. Of course, that's represented in this equation by the equal sign, right? Energy is equal to mass times the speed of light squared. That's what E equals mc squared really says. We're not going to go into the details of that in this particular course, but again, most famous equation in physics, you've heard of it before, and it's the definition of physics. And now, when we think about the matter side of physics, right, we think of studying materials. We might think of chemistry. Perhaps you took a chemistry course before you took this one. Chemistry is very closely related to physics. It's the study in particular of very small matter, matter at the atomic or molecular scale. We will spend more time in this class talking on larger scales about matter. We will be more interested in kilograms of stuff than in grams of stuff like they are in chemistry. But we'll be studying the matter and, of course, the energy. And a big part of energy is motion, which is where we will sit for the majority of this class, is studying the motion of things around us and how can we understand that, how that works in our universe. So fundamentally, physics is the basis of all the other natural sciences, right? We have the broadest definition, right? Biology is the study of living matter, and chemistry is the study of molecular and atomic matter and energy. Geology is the study of rocks and the history of the earth and that sort of thing. Astronomy, obviously the things off of the earth, the stars, the planets, all of that. But all of that really does fall under the category of matter and energy. In fact, you're hard-pressed to find anything in the science realm anyway that is not falling in the category of matter and energy. There are other fields. Obviously, when you went to school, to high school, you took more classes than just science, right? There's language, there's social sciences, there's other things. But within science, everything really falls under the umbrella of physics. So as I go on in this presentation to talk about why we study physics, in sometimes it's kind of general, why do we study science in general? But all of science falls under physics. So as it says, sports to technology, we use physics all the time, right? If we think about sports, sports are all predicated on movement of some kind, whether it's the individual that's moving or the ball that's moving or both that's moving. Sports would be really, really boring to do and to watch if there was no movement going on, right? Watching paint dry, people joke about that, right? But there's nothing going on when paint is drying. There's no motion, and that's part of why it is so boring. Some people claim fishing is boring too, because there's not very often motion or very much going on. It's part of that's your preference, right? So from sports technology, we have physics, the motion, certainly for the sports technology, it goes far beyond the motion. You see there different types of phone technology, which has become very big in recent years, how we communicate and all the incredible things our smartphones can do for us. And all of that is predicated on the technology that we get from physics, the touch screens, the technology to access the cell towers and the internet and all of those things, the cameras even inside of our phones, all of that is ultimately physics. And then we think of things that maybe come to your mind more when you think about science, the idea of robots, what they can do for us, how they can walk, how they can do things that do things for us as humans, or do things that would be too dangerous for us to do. So lots of different examples. So how does the physics itself work? There are really two sides of physics, two sides really of all sciences, but we're talking from a physics standpoint. There's the theoretical side, and that's where Einstein sits, right? That's where Einstein and Newton and many of the names that we're very familiar with reside. And that's where you come up with the models of how the world works. Again, the world is incredibly, incredibly complex. The universe, incredibly complex. We have a lot of trouble trying to understand it. And so we simplify it, and we come up with a model that we think will explain a certain part of it. And that's the theoretical physicist's job, right? Even E equals mc squared was Einstein's model of how matter and energy could be converted from one to another, and how much of one it would take to get some of the other. That was a model. And they come up with these models of the world. Now, they don't come up with it out of nowhere. Einstein did not come up with E equals mc squared out of thin air, right? He's looking at data. He's looking at information we have from other experiments we've done. But they come up with the models. The theoretical physicists come up with the models. And then we have the experimental physicists, and their job is to test the models, right? Einstein says E equals mc squared. And so an experimental scientist says, that's interesting. Let's see if I can take some matter and turn it into energy and see how much energy I get. See if his model works, if his equation is correct. And so the experimental physicists are usually what you think of more often when you think of scientists. You think of them being in a lab. You think of them wearing white lab coats and safety goggles and mixing chemicals or doing stuff and writing down data, right? That's what you did in high school in science class. You did labs, and you had to collect numbers based on what you did in the lab. And that's the experimental side. And they really go together. They have to go together. They have to fit together, because without the experiments, we don't have any data to inform our thoughts on what the models might be. And without any models, we don't know what to experiment on. We don't know what to test. We don't have any equations for us to go out and say, hey, is this really how the world works or not? And sometimes it is the way the world works, and a lot of times it's not. Almost all of our models are wrong to some degree. Most of them are very good. They're right most of the time, but we do not have perfect models that match the world completely. And so we continue to experiment, and we continue to test them, and usually we don't throw them completely out. Usually we just have to change them some to fit the new data and to make them more accurate to the real world. So you see there the idea of trying to confirm or refute the models. And the most exciting experiments really are the refute ones, right? I mean, when Einstein says E equals mc squared and we find out that it's correct, that's exciting for Einstein, and it's exciting to a degree, but it's much more exciting to break the model, to say, haha, you're wrong, theoretical physicists, you got to come up with something new. And that happens on a fairly frequent basis, especially in areas where we don't have a long history of model and experiment, because these two go together and they reinforce one another. Here we have a quote from a physicist speaking about when we were first coming up with atomic models and that sort of thing, which really was not all that long ago, right? Niels Bohr and Heisenberg, and those guys were we're roughly 100 years ago at the beginning of the 20th century coming up with the proton, the neutron, and the electron. And we learned those things in chemistry, and the chemists act like we've always known about the electron, proton, and neutron, and the periodic table and all of that, but it's really fairly recent stuff. Most of what we'll learn in this class is way older than that. We'll talk a lot about motion and Newton's laws, which is 300-400 years old instead of just 100 years old. So what do we care about science? Why do we care about how the world works, right? If I'm not going to be a physicist, why should I care? You know, what do I care about all of that stuff? Well, you care because science immensely affects your life, and it affects your life through technology. So science, technology, those two words, maybe some people think they're interchangeable. They are really very closely related. As it mentions on the slide, technology is the application of our knowledge of science to real world problems. So give an example of this, right? So we're trying to grow better crops, and we're having trouble feeding our country or our community or our world, however you want to think about it. And so what we do is we study how plants grow, we study what causes them to grow better and what causes them to not grow as well, and we come up with models of how plants grow and what helps them to grow. And then we turn around and we take that information and we share it with farmers, and we say, look, plants need nitrogen to grow, nitrogen in the soil, and they need water, and they need carbon dioxide from the air to grow, and this is what they need. And so scientists and the farmers then take that information and they formulate fertilizers to use on their soil to make the plants grow better. So our understanding of how the plant grows allows us to turn that into technology, in this case fertilizing technology, to allow us to grow more food more effectively and benefit society in some way. So here I've got a whole list of physics ideas. Primarily they're on the left side, they say science, but they're really all physics, and then what we've come up with to use them, right? So we'll talk about Archimedes' principle in chapter 13. It's basically the principle of flotation and how things float and why things float, and that's led to our construction of boats. And to be able to build boats out of many different materials and to have confidence that they're going to float, because we understand the principle, which we call Archimedes' principle, behind buoyancy force and what's necessary. At the University of Illinois, when I was a student there, the civil engineering students were required to build boats out of concrete, which might sound pretty ridiculous, but if you understand Archimedes' principle, you can build a boat out of concrete that will actually hold a person, and it can be done if you understand the principles, even though we think of concrete as something that sinks. So you can go down that list, and I'm not going to articulate all of these, but the point is we take the science and we use it to do something very practical for our lives, like computers and iPhones and semiconductors, nuclear power plants, cars, all that good stuff. So who does this technology thing? Well, we tend to think of people like Einstein and Newton as being the scientists. They focus on figuring out how the world and things around us work. And then we have the people we call inventors. They take that understanding of science and they turn it into practical, useful things for our everyday lives. Thomas Edison, probably one of the most famous inventors of all time. He would probably tell you, if he was alive and you could interview him, the reason he was able to invent so many things was because science had figured out so many things in the decade, the century before he was living. And so there was a lot of new science just sitting around waiting to be applied to our everyday lives. And of course, most famously the light bulb, but many other things. And he had a whole lab and a whole set of assistants helping him invent many of these things that were very beneficial. But you got George Washington Carver there too, did a lot of agriculture research with peanuts and different things that could be grown in different soils and with different conditions. Benjamin Franklin, a little bit longer ago, right, with the bifocals and the Franklin stove, and a number of other just very simple and practical hands-on things that he was able to invent to make our lives easier. And then someone obviously much more current, Steve Jobs, with the iPhone and Apple and the advent of technology that, you know, some people look at it and go, well, what benefit is that? But when we look at the incredible productivity increases we get from the personal computer and from the smartphone and these things that allow us to accomplish things in far less time and far less effort, and how that frees up time and resources and effort to do other things. These are things that are benefiting society. As I mentioned, there's a lot of, I talked about the cyclical nature between theoretical and experimental, where the new models lead to new experiments. But we also have that cycle going on between the science and the technology. As our science helps us to understand the world better, the technology, then the application of that science as technology allows us to do our science even better. So one of the great examples of that are right there in the middle, the telescope and the microscope. As we understood lenses better and were able to use them to magnify things and to look both into the distance with magnification and into small things with magnification, we learned immense amounts of things about our world, right? We know the story of Galileo and looking at the planet Jupiter and seeing the moons going around Jupiter, and how that allowed him to make great strides in understanding how our solar system works. And obviously the microscope and cells and understanding microbiology and how people get sick and how people don't get sick, and all of those wonderful things that would not be possible without those simple lenses from the lens laws of physics that are further back in your book. We won't get to them. Again, one of the downsides of physics is that it is an immense subject with a lot of different topics, and we can't cover them all in one semester. But that's one of them. The robotic rover there on Mars is obviously a robot that is self-driving and is powered by solar panels and is incredible, but it is rolling around on Mars collecting data about Mars, which is teaching us about Mars, also teaching us about our planet, right? Because if all we have is the Earth and all we have is information about the Earth, that's only one data point. And as soon as we start getting information about Mars and Venus and other planets that we could collect information from, that helps us to understand what's uniquely Earth and what's more generally about planets, and that helps us to get better models and to be more accurate. Obviously, computers allow us to do calculations and modeling that would not be possible without that computational power, and lots of other examples here as well. So how does this really make our everyday life better, right? Is it really better, or is it just different? You know, would you rather live today or 200 years ago? Isn't it just that we're busier today and we work more hours and it's no fun? Well, I have several examples here of really sharp differences that technology has made for us. The first one is transportation. Those are the pictures already on the screen. We got the Alton Bridge there, the Clark Bridge in Alton, which allows us to cross the Mississippi River. Obviously, immense amount of concrete and steel and all kinds of physics that goes into being able to build a bridge like that. And without all of that physics and applying that physics as technology, you're back at rowing a boat across the river, right? Which takes a lot longer and more physical effort and is less efficient. You got the cars there. You know, I show my children on a map where their grandparents live in Ohio, and you know, we talk about how we go in a weekend to visit their grandparents that are 500 miles away, and how this is a measurable, visible distance across the globe that they can see on a little globe. I mean, it's just crazy. You think 200 years ago, when you were traveling at the speed of a horse, 500 miles would take an incredible amount of time. And then you go down a step there to planes, and it's even more significant. Life expectancy. We got a life expectancy 1820 to 2003. Obviously, we're in 2020. The life expectancy continues to rise. The blue line is developed nations. The red one is everybody. The green one is developing nations. But even if you take the developed nations, the best case scenario in 1820, the life expectancy was less than 35 years. Less than 35 years. That's frightening. I'd already be past the life expectancy, and I still feel like I'm pretty young. And then you go down, the other two lines are below 30 years. So people just didn't live as long, in part because of disease that we didn't understand, in part because of food production that we didn't have, in part because of making a living as a miner or a logger or all kinds of farmer. All these things were much more physically demanding on our body because we didn't have the tools that help us out today and make life easier. And so you can just see there, over time, we now get to 2000 and we've got life expectancies above 70 years, approaching 80 years of age as a life expectancy, as an average. It's pretty amazing to think about it, and I attribute all of that really to technology. And you can sit there and talk about politics and global conflict, and ultimately technology is part of what has made us wealthier and therefore less likely to fight with one another because we have more to lose. And finally, the food, right? And that's part of the life expectancy as well, which does all come back to the technology and the science. We eat better than they did in the past because we have the ability to not only grow more, but to preserve it and to transport it across the planet. We will talk about how refrigerators work. We will talk about why they work. We will talk about how that has incredibly benefited society as a whole, but that functionality of a refrigerator is entirely and completely physics, which we will get to there in chapters 14 and 15. But you see there the picture of the combine and the tractor, of course, emphasizing how much can be harvested in a short amount of time by a few people compared to the past when it was done by hand. But also the fruit salad, right? The whole idea of having a fruit salad, the very idea that we have a concept of fruit salad, right? Without the ability to transport food around the world the way we do, you would be eating whatever fruit was currently ripe in your corner of the world, and that would be it. You'd be eating apples and only apples, or you'd be eating peaches and only peaches. But we can eat apples and peaches and grapes and bananas and kiwis, all these things together at once because of our technology to be able to transport it and to grow it. There's lots of science that we aren't using yet today. We're working on it. Some of it we're getting closer, some of it not. Superconductors is something we've known about for 40, 50, 60 years now. Haven't quite come up with a ton of great applications. Obviously, the CERN collider over in Europe, where they recently discovered the Higgs boson, uses superconductors to get to those high energies. So there are applications, but not in everyday life. We're hoping maglev trains reduce friction even more, make transportation even more efficient and less energy, and therefore ultimately less cost. Some of the uses are more exotic, right? We'll talk about angular momentum. We'll talk about something that spins and keeps spinning in the same orientation. It happens in as common of things as bicycles and as complex of things as the gyroscopes that power and help the spacecraft to navigate themselves and help the Hubble Space Telescope to know where it was pointing so it could take good pictures. But all that's the angular momentum that we'll talk about in chapter 9. So here we got a list of the branches of physics. Like I said, it's a large subject, and there's a lot out there. We are going to be covering just a few of them this semester. The ones that I have highlighted in red are going to be the ones we're going to touch on. And mechanics there at the top, it's always the one you learn first in physics. It's the basis of many of the others. It's the basics of motion and mass. And a lot of the others go into it in more detail in a specific situation. But we're going to go beyond mechanics. We're going to talk about thermodynamics too, temperature, how that affects matter and the states of matter. Solid state physics, we'll talk about solids, and then fluid dynamics, we'll talk about liquids and gases and how that interacts with temperature. So those are the 4 areas we're going to cover. But again, mechanics will be the main topic. Chapters 1 through 11 are mechanics, and then 12 through 15, we talk about the states of matter and the thermodynamics. So there we got one more slide. I forgot about this one. Important slide, shouldn't have forgotten about it. The process of science, like I mentioned, it's cyclical between the theory and the experiment, but we come up with these models of how we think the world works, how we think a little piece of the world works, and then we test them. And as we test them, we find out that they're wrong and we need to change them and adjust them. There's a lot of confusion about theories and laws and principles. The principles and laws tend to be much more basic, much simpler. They're just trying to relate 2 items typically, or 3 items in a very mathematical way. And those rarely change, right? We talk about Newton's second law, F equals ma. That's mathematical. It's very easy to test and measure. And so that's probably not going to change. Although we thought we thought Newton's gravity was very solid and not going to change, and Einstein found a way to explain to us that it wasn't quite right. So the principles and the laws rarely change, but the theories, which are more general and are trying to explain a large area of the universe instead of just one tiny little corner of it, those are much more prone to change. Theories do not become laws, and laws were not once theories. That's not the relationship. I still think we get confused because we all watched Schoolhouse Rock in grade school about how a bill becomes a law. And that's true. Bills become laws in Congress, but theories do not become laws. That's not how it works in science. But it is recursive. We go back and forth, around and around, testing the models, trying to get them stronger and more reliable, so that we can understand the world better. And then we can take that understanding and apply it to the problems of life, which we call technology. Is when we find a solution to a life problem using our understanding of science, and that makes our world better. So that's why science is important. That's why we want to understand it. It obviously continues to come up in our world continuously. We continue to have new technology, and we need to be educated citizens to be able to analyze whether this is good or bad, and also to be able to understand the underlying principles. So that is the end of chapter 0, and I will see you when we discuss chapter 1.